Welcome back, physicists. I think we have a short lesson today. I think this one should be real quick, in and out, no crying, no tears, and I think the goal of this lesson is a lot more straightforward than it was last time. So I think this one should be a little more grounded and a little more in your kind of ballpark. So um, allow me to help you try and understand how to use uniform circular motion and force diagrams together to solve problems a little bit better. So, what we're going to talk about today is why do I get the feeling my pen's not working? It never is. How to draw force diagrams for uniform circular motion and set up the corresponding sum of forces equations. This is going to be intentionally left pretty simple. We could do some harder ones, but I don't think that's a good strategy for instruction because then we get bogged down in like math and stuff, and we're not really looking at the physics underlying all the math you're getting bogged down in. So, we're also going to look at how to make predictions about the change in variables. Sorry, how changing variables will affect a system. So when things are going in circles, there's a lot of different things to consider. There's the mass of the object going in a circle. There's how fast it's spinning. There's how big is the circle itself. There's what forces are acting on the system. So there's a lot that goes into it. And we could change realistically a lot of those things. We can make things heavier. We can make circles bigger. We can make objects faster or slower. All of these things are going to affect the whole system. So we need to be aware of how those things interact. So I have basically one example for you that's got a lot of different parts to it that kind of go through all these different topics of uniform circular motion and force diagrams to hopefully help us understand what's going on, how to set things up, and how to solve problems. So, without further ado, let's remember what we already know. Uniform circular motion means that there are two very specific things happening. An object is going in a circle, not an ellipse, not a hyperbola, not an oval, not a kind of lumpy circle, a circle. The speed of the object is also constant in that circle. Again, I'd like to highlight the fact that I'm using the word speed here instead of velocity, because if we're going in a circle and we're spinning, the direction is changing all the time. So the velocity is changing all the time because velocity depends on direction as well. So we're just talking about if I were driving a car, what does my speedometer say? Not necessarily what does the directional heading say also. Okay. Keeping in mind these two properties of uniform circular motion, we also need to remember a general equation. For objects to stay in uniform circular motion, the net force on the object must take the form mv squared over r. If it doesn't follow this formula, and not a lot of things have to, they don't have to do this, right? They could weigh more, they could go faster, and they could have a different radius, or the force could just be a different number. That will make it not circular motion, or rather not uniform circular motion anymore. For it to be in uniform circular motion and to stay that way, it has to follow this equation. And this sum of forces must always point towards the center of the circle. So if you do another problem and the number just happens to work out to whatever this number is, but it's not pointing towards the center of the circle, maybe it's pointing away, then it wouldn't be going in a circle, obviously. But I'm not going to try and fool you with that. You know what I mean. I'm going to be pretty honest about it. Okay, so let's go look at this beautiful example that we've concocted. I've tried to pick a very real life scenario so that it's easy to see a real situation or something we're familiar with. I find that if we pick a topic that's too like out there, like space stations orbiting stuff, or you know what I mean, like things that you probably aren't very familiar with or haven't experienced, then it's a little harder to like wrap your noodle around it. So we'll wrap our noodles around something familiar. So it's my hope that all of you have ridden a bicycle. If you haven't ridden a bicycle, I really recommend it. It's one of my favorite pastimes. I legitimately and honestly love riding my bicycle. It's super fun. It's so relaxing. It's a great way to get out there, get some fresh air. Uh, but I digress. You know, I'm not trying to make you all bicycle lovers, but it would be cooler if you were. So the problem we're going to look at first is I've entered a bicycle race, and one of the turns of the race is a circular U-turn. So kind of picture this. Here's the inside of the track. Ooh, hold on. Hold up. I can do better than that. And then here's the outside of the track. There we go. So this section here is very much a circle. That's how I'm trying to frame this question. So for this part of the track here that we're looking at, I'm going to try and follow this blue line as best as I can. I don't want to get too close to the inside or the outside. I might fall and hurt myself. You know, I'm delicate. What we want to start by doing is drawing a force diagram for myself and the bike. And I'm gonna toot my own horn a little bit here. I have a really cool bicycle, and I have a set of pedals where my shoes like click into these clamps and attach to the bicycle. So for simplicity of the problem, we're gonna treat me and the bicycle as a single solid object, because really when a person's in the heat of the moment and they're in the race and they're putting the pedal to the metal, so to speak, you've got to be one with the machine, you know. uh Plus I'm attached to the thing, so it's just easier, right? um so yeah. All right, so let's draw a force diagram for me and the bicycle. Here's maybe a top view. There's my handlebars. I'm on this thing, we in it. And then I've got like a little tire here and maybe a tire here. Yeah, anyway, so there's my bicycle, there's me. What do legs look like? I don't know. Anyway, you get the idea. So we're going this way. So we're gonna do a rear view, like you're looking at my bottom. Let's draw a force diagram. Obviously, we have the coward's force, weight. That's always the one that like every single student says first. So I'm like, you're a coward. You didn't do anything adventurous. You gave me the obvious one. There's always weight, chicken, but you know. To counteract the weight, because obviously I'm not falling into the asphalt, there must be some sort of normal force up on my bicycle from the ground. So we'll put that straight up. Normal force from the ground. And then what is the force that is pulling me towards the inside of the circle? There must be some force pointing towards the center of the circle to keep me going in a circle. What is my bike being pushed by or pulled by towards this direction so that it doesn't just keep going that way with me on it? My bike, luckily, has very grippy, nice rubber tires on this very grippy asphalt, scientifically engineered to grip rubber tires very well. So that grip between my tires and the ground is friction, and friction is always parallel to the object or surface that you're rubbing on or trying to slide on. So friction is going to be this direction, towards the inside of the turn. All right, wonderful. So this is the force diagram for me riding my bike around a circular turn. It's wonderful that friction is perfectly horizontal and the other two are perfectly vertical. So we can use Newton's first law to say that these two are going to be equal, because I'm not going to accelerate up or down, hopefully, while I'm riding my bike. And we can see that we have an unbalanced force in the horizontal direction because I need to accelerate. If I'm going to go in a circle, my velocity has to change, which means I need to accelerate. To have an acceleration, we have to have an unbalanced force. So here is my beautiful force diagram. Let's go ahead and write the sum of forces equations in the vertical and in the horizontal directions, just so that we can have them kind of for completeness. This is a step you should always take when doing any force problem. It should be habit. It's like in your math class when you see a polynomial, hopefully you have some sort of like overwhelming urge to factor that polynomial. Same thing here. You should have an overwhelming urge to set up a sum of forces equation. So let's do the vertical direction first. So sum of forces, I'm going to say the y direction. We'll say up, down is y. Up being positive, down being negative. Our sum of forces in the y is going to be my normal force, positive because it's up, minus because it's down, my weight, equals 0 because I'm not accelerating in the vertical direction. In the horizontal direction, my sum of forces in the horizontal direction is just my friction. So we have only friction equals MA because it's unbalanced. So we have to have it, Newton's second law says we're going to have an acceleration. So equals MA. And because I'm going the same speed, I'm going to kind of coast through the turn, and I'm going in a circle, we can also say that this is equal to mv squared over r. And we can sort of see that A is equal to v squared over r. V squared over r is the equation for the centripetal acceleration in uniform circular motion. We slap a mass on it to turn the acceleration into a force. So now that we have our force diagram, we've labeled confidently with names, no force applied, no invisible forces, no net forces. We've labeled confidently, clearly, and I'm sure there's another English word we can throw in there about it. Neatly, I don't know. And we've written our sum of forces equation. I think we're prepared to actually start doing whatever problems may be asked of us on this problem. Okay, this is a solid first step for any force problem, and we've done it beautifully here. All right, question 2. I've told you that we're going to look at the same problem through the whole set of notes so that we can keep a coherent idea going. So we're going to derive a formula for the maximum velocity on the bike in terms of the mass of the bike and the rider, so that's me and the bike together, the radius of the turn, the coefficient of friction, and any other physical constant. So this could be the force of gravity or the acceleration due to gravity, g. It could be, that's pretty much all I can think of that would really apply here. But any physical constants like the mass of a proton, the mass of the Earth, any stuff like that. But probably just lowercase g, the acceleration due to gravity. So let's go and try and do this. So if we're going to derive anything about this situation, the only way we really have to really solidly describe this right now that we've talked about is this set of sum of forces equations. So because they're asking me for a velocity, we're probably looking for that thing right there. So let's use the sum of forces in the x direction. So our sum of forces in the x direction, it's just friction equals I'm going to omit the MA. That's not really important here. We're probably using the MV squared over R because we're looking for that velocity. So MV squared over R. All right. It says derive a formula for the maximum velocity. Okay. So at some point, I'm going to be going too fast and my bike will just slip out from under me, right? What that situation would be is if friction is not strong enough to give me this required amount of force. If friction's too weak, then I'm just not the wheels can't push to this the center hard enough, and my bike is going to end up sliding. It's going to turn it from static friction to kinetic friction, which will be bad. Okay, so it doesn't ask me to solve in terms of friction. It says I can use the coefficient of friction, but not the force of friction itself. So let's make a substitution here. Let's substitute our friction, and this is static because I'm not sliding. Let's substitute that out for the equation we know for static friction, which is going to be mu times n. Okay, equals mv squared over r. Here, it doesn't tell me I can use the normal force either. It says in terms of the mass of the bike and the rider, the radius of the turn, the coefficient of friction, and physical constants. Normal force is none of those things, so I can't keep my normal force in here. I need to substitute that out with something else. I need to get rid of it. So if we go back here, we can see our normal force is equal to the weight. You're going to say, Mr. Barton, it doesn't say weight either. But weight is mass times gravity. So we're going to substitute our normal force out for mg. So we're going to have mu static times mg equals mv squared over r. And let's see. Am I using just the variables they asked for? Coefficient of friction, good. Mass, yep, that sounds good to me. G, that's a physical constant. Mass again. Velocity is the thing I'm looking for, so that's fine. Radius of the turn, right there. So all of these are allowed variables. Now all we have to do is isolate the velocity. Sorry, I shouldn't circle the two. We want the velocity, not the velocity squared. So let's multiply both sides by r. And then let's also divide both sides by m to get this m away from it. Okay, so the r's here cancel, the m's cancel. This mass, this is the mass of the thing going in a circle. That's me and the bike. The friction is using the normal force, and the normal force is equal to the weight. The object's weight we were talking about is me and the bike. So these two masses are the same thing, so they're going to cancel each other out. And then the last thing we need to do is take a square root to get rid of this squared. So we'll throw a square root on there. So we can simplify this to the square root of the radius of the turn times the coefficient of static friction times g equals the velocity of the bike. So this is constant. This is a property of the tires and the road. And then the radius could change a little. I could maybe get a little closer to the middle of the turn. I could get a little farther to the edge. That one's a little variable, but my velocity is limited by these things. If I want to go faster, I need more friction, more gravity, or more radius, meaning a bigger circle. Okay, so there we go. This is our equation for the maximum velocity of the, of me going around the turn. Okay, all right. Cool, we've done it. That was a fun little math problem. Now let's see what else they have for us. I have a combined mass of, it looks like they're giving us numbers. So we're going to use our result here, this equation. So let's write it down. V max equals the square root of r mu g. Okay. Wonderful. So they're going to give us some values, and we're going to just plug them in. What's interesting here, I have a combined mass of 78 kilograms. Mass doesn't show up here because our friction depends on my mass, because it depends on the weight. The more mass I have, the more weight I have. And we also have our mass over here for our centripetal force, and they canceled out. What's very interesting here is my velocity does not depend on my mass. So what that means is my maximum velocity is the same maximum velocity as a really big rider who weighs a lot more than me. Maybe this is their first race and they're not quite as lean and, lean as myself. Or maybe they're very lean and they're a professional cyclist, because I race in professional category cycling, and they're like 3% body fat, so they don't weigh as much as me. They don't have quite as much muscle. But all three of us, the skinny professional cyclist, myself, the athletic build, and then the slightly bulkier build, all have the same maximum velocity because our friction has helped us cancel out the mass, and our max velocity is independent of mass. So skinny people and heavy people can all go the same max speed before their bike slips, which is maybe a little counterintuitive, but interesting. Okay. So this is irrelevant information for us. Here's the relevant stuff. The radius of the turn is 5. The coefficient of friction between the bike tires and the ground is 1.1, unitless because it's just a scaling coefficient. And the max speed is what we're looking for. We know G. We'll use our usual 10. So let's plug these in and then hit it with a calculator. So our max velocity equals the radius of 5, coefficient of 1.1, and then G is 10. So 10 times 1.1 is 11, times 5 is 55. So square root of 55. And then we'll put that into our calculator, and it's going to be a little under 7, or a little over 7, I think. Yeah. So our maximum velocity is 7.42. I'm rounding up a little bit here, meters per second. So if I'm going faster than that, that's about 15 miles an hour. If I go faster than 15 miles an hour, I come in real hot, 25 miles an hour. I'm going to slide out, and then I'm going to have a real bad case of road rash. So there we go. There's our maximum velocity. Pretty fun. Okay. Let's talk about this just a tiny bit more. I keep saying it's the maximum velocity. What would happen if I didn't have this velocity? So if we go back here, there is maybe an equality that should be an inequality. Our force of static friction, remember, the force of static friction is less than or equal to mu s. So what would happen if I wanted to go in the same circle but slower? I'm scared. I'm too chicken to go the full 7.42 meters per second in such a tight circle of 5 meters. This is about 15 feet. Going almost full speed on, maybe not full speed if I've got to keep my reputation intact, but going this fast in a 15-meter circle, in a 15-foot circle, that would be incredibly scary. This is pretty fast. This would be like if you had your friend pull you like in their car, you're holding on and you're riding your bike, and then you let go, and then you try and make a turn around like a corner of the street. Going that fast is incredibly scary. So if we're going slower than this, this will drop. our net force required to go in uniform circular motion will drop, that's fine. Can our force be smaller? Is there a way that our friction can be lower? Of course, because it's an inequality. So it will just automatically adjust itself. The force of static friction is very much like the normal force, where it just is whatever it needs to be to balance things out. Until you reach the or equal to. And then if you go over the or equal to part, then you're going to slide out and turn into kinetic friction. So if our speed drops, that means our net force needs to go down as well. And our static friction, because it's this inequality, it's allowed to just automatically decrease itself and it will adjust itself. The or equal to, when you use the or equal to, you are actually finding static friction maximum. This is the biggest your static friction could possibly be. So if you go beyond that, you're going to start sliding and you're going to turn into kinetic friction. Okay. Last question. And this is just a test of proportionalities and things of that nature. This is to make sure that we can kind of manipulate equations and logic our way to an answer. So it says, what would happen to the max velocity if the radius of the turn increased? So let's look at our equation. Our V max that we derived is equal to the square root of R G mu S. So if my radius of the turn increases, because this is in the numerator, or it's not in the denominator, if this thing goes up, so does this side of the equation. So if I increase the radius of my turn, then the net force goes down. The force required for me to be able to go in the circle goes down, which means I kind of have more extra friction laying around. So looking at the equation we derived, if friction goes up, if radius goes up, velocity max increases. The max velocity would also increase. Okay. What would happen to the max velocity if the coefficient of friction decreased? So if this value goes down, our maximum velocity is also going to go down. The way we would explain that is if my coefficient of friction is smaller, I don't have as much friction. The road is slicker or slipperier with my wheel. If I have a slippery road, I need to slow down, otherwise I'm going to slide. So if our coefficient of friction decreases, the max velocity also decreases. Okay. And then lastly, what would happen to the maximum velocity if the mass of the system increased? We can see from this equation that we derived that our max velocity is independent of mass. Mass doesn't show up here, it canceled out. Meaning, if I change the mass of this system, it has absolutely no effect on my max velocity. Keep in mind, this is not true in general for all circular motion. This is only true because the force making me go in circular motion is dependent on the normal force, and the normal force in this case was equal to the weight, which also depends on mass. If our force causing us to go in a circle was, say, tension instead, then tension in a rope is not going to depend on the mass of the thing on the end of the rope. The rope doesn't care how much mass is on the end of it. It just pulls as hard as it can, and then our mass would change. But in this case, velocity is independent of mass. Okay. So I hope that this has been helpful for you in seeing how to set up an equation or a force diagram using circular motion. The really, really important part when we're doing circular motion is realizing that instead of using MA, we're probably going to want to use the form MV squared over R instead. That's generally the only unique thing about forces, force diagrams, sum of forces equations for uniform circular motion. Um, okay. Hopefully, this has also made you a little bit more comfortable with deriving a formula. I think that's one of the, I don't want to say the first time we've ever had to do that, but it's been a little while since we've done that. So it's always good to practice our manipulating equations without putting numbers in. Sometimes I feel like we look at a little too many problems like this, where number, plug them in, beat it to death with algebra, calculator, ta-da, there's your answer. Sometimes we kind of just need to take a step back and look at the equations and really describe what's happening in the system and see if it makes sense to us. Okay. So, let me know if you have any questions or any comments, concerns in the comments below. Make sure you hit that bell icon if you want to watch your notes like the night before class. You'll get a little alert that says I uploaded a new video. Till next time, have a wonderful day. Stay out of trouble. Stay safe, everybody. I'll see you next time.